Okay, this is section 2.2 of Unit 2, and it's about intramolecular force and potential energy. Now, in intramolecular forces and potential energy, it's just about the forces that are attractive or repulsive between molecules. Think about them like magnets. These forces aren't as strong as actual chemical bonds, but they help explain boiling points, melting points, solubility, and that kind of goes back to the lab that we did where we checked out some boiling points, some melting points, solubility, and able to conduct electricity. And so the big idea here, I bet the first thing that they mention, and I'm right, is Coulomb's law. And Coulomb's law is just, the attraction force is equal to or proportional to the charge of the first atom, the charge of the second atom, divided by the radius or the space between them squared. And yeah, so if Q1 and Q2 is negative when you multiply them, the interaction is attractive. And then we kind of see that here. I don't know if I can zoom this in anymore. Hopefully I can. It allows me to zoom out, but does it allow me to zoom in? Yes, it does. Here we go. And as you see this is where we want to be. This is optimal, right? And this shows that the Q1, Q2, or the multiplication of the two charges is a negative. And so that means the interaction is attractive, giving negative potential energy. And as the molecules get closer, the energy becomes more negative, meaning that the attraction is stronger. And we see that here. It's at negative 432 when the distance is only 74, right? And then as we go up here, as the distance r increases and increases, the potential energy decreases and decreases. If you get too close, however, then repulsion takes over. And here's an example of that. Here they are too close, and then now they're repulsed, right? Like, think about it. Like when you're repulsed by someone, you're not attracted, right? So, yeah. So how does this affect what we are learning about, and how does this affect intermolecular forces? Here, 1 second. Here we go. So another thing that we notice is, so for example, halogens, they all have the same effective nuclear charge of 7+ due to their inner, their valence electron shell. And so we see here Cl2, Br2, and I2. And if we look here at a periodic table, Cl2, Br2, and I2, they are in order of size. So one gets larger and larger and larger. So as this size increases, because each one has one more electron shell, we see that the radius is increasing, which makes sense. As the shells increase, there's more shells, and so there's more space, right? But as the shells increase, the bond energy decreases. The force of attraction decreases as there is more space. Now, this is kind of like holding a magnet, right? If you hold a magnet and the magnet is pushed further and further apart, then it's not going to have as strong of an attraction. So the big idea is really this. As the radius increases, the force of attraction decreases. So they are essentially an inverse relationship. And potential energy becomes more negative as they get closer. So as they get closer, the bond energy or the potential energy increases. As you see here, R goes from 266 to 228 to 119. They're getting closer, and so the potential energy or the bond energy increases. Okay, so let's look at the first question. Okay. Here we talk about a single bond, double bond, triple bond, and it would make sense that a single bond, its energy would be less than a double bond, right? The bond energy would be greater, right? Because think about it, if you had two people holding one hand here together, it would not be as strong as if they were to hold two hands together. And so here's just one, and here is two, and here is 3. And so with that, right, single, double, the energy here is increasing. The bond energy is increasing. So look, the force is increasing as we go down, right? But then what happens to the bond length, aka the radius, right? And so naturally, it would decrease, right? As there's more connection, the radius would decrease. So here it says force would go down as the radius would go up. Yes, and so the inverse, they are inverse. So if you looked at it this way, from bottom up, the force is attractive force is going down. So the force is going down. If you look at things, if your eyes are looking up this way, right? So the force is going down, and as the force goes down, the radius or the distance between is going up. And the opposite is true, which is what I'm looking at it actually from, here's my eyes, right? I'm looking at it, looking down. And I see that as I go from single, double, triple, it's the same thing. It's just reverse. Here's like, it just means wherever one goes, the other one will go opposite. And I thought that was pretty intuitive. Okay. And so here they just talk about how so here what we were talking about earlier with as the charge is negative, they are more attractive, and so the potential energy is more negative, meaning that they have an attraction. And so if there's too close, that's also an issue, and they're too far, the potential energy decreases. Okay, so let's look at the first question. I wish I could just... Okay, boom. So this graph shows you like a classic potential energy curve, like Leonard-Jones. That's what they call it, a potential energy graph. And so the bond length, so the internuclear, right? Because that's it's not the best line. Okay, so the internuclear distance, excuse my stylus, is basically the bond length. So you should be marking up your paper as I am. And so that basically that's what they're asking for. And if you look here, you find the bond length at the minimum right here. You find the bond length right here. And if you look here, the bond length, I would say, is about 75 picometers. And so I am, I have no choice but to pick B, because B shows that, the atoms form with a bond with a length of 75 picometers. Okay. Next question. Hopefully we can get all of it in the screen. It's not the best. Okay, hopefully that works. Which of the following graphs correctly shows the relationship between potential energy and internuclear separation for two hydrogen atoms. So that's H2. So because this would be a covalent bond because there's no difference in their electronegativity. So it would be H. They would equally share this electron. When they're close, first it has a repulsion that is pretty high. So the repulsion should start off here for when they're too close, like the other graphs that we looked at earlier. And then there should be a drop down. So it should start off something like up here, and then there should be some type of drop down like before, and that's the optimal bond, right? And that represents like this right here represents the bond that is most stable. Like we've seen before. And so normally, and then it would normally gradually go up and kind of level off, and this would be, my lines are the worst. It's not like I have a ruler here, by the way. So there's like a line that goes across here, and that would be like 0 potential energy, and this would be negative, and right? And so it should look like that. So now if we evaluate all of these, right, I would off the bat say it could not be this, it could not be this, could not be this, and this one, there's no scenario, I don't think, that it goes and it becomes positive again, right? Because what would happen is just the hydrogen and the hydrogen would be far enough where it would be like somewhere here, so it wouldn't go back to being positive. So I think D is the only answer that it could be. Because here we have when they are too close, here, and this is a class example. When they are too close, here they are when it's ideal. This is the ideal distance. And then here is when they are kind of slowly, moving apart. So I think the answer is D, and this is kind of like a classic example, especially with a diatomic atom. Okay, next question. Okay. So this graph shows 3 different diatomic molecules. So let's read the question. The potential energy as a function of internuclear distance, right? That just means like bond length, right? Internuclear means inside the nucleus, right? Distance for 3 diatomic molecules. 3 diatomic molecules, and these are the 3 diatomic. Remember, I taught you all the diatomic molecules, and then I showed you the acronym. Never have fear of ice cold beer, right? So that's nitrogen, hydrogen, fluorine, oxygen, iodine, chlorine. Don't mix this up for carbon, and Br for bromine. So these are all the ones that can be like N2, H2, F2, O2, I2, Cl2, and Br2, right? So like beer, right? Never have fear of ice cold beer, right? And so the data shows in the graph, it shows the diatomic molecules and how they are going about their their potential energy for their bonds. So what it shows off the bat is this one is it ends up here, this one is down here, and this one is here. I would think that's the most important information. And so this one is approximately, let's say, like 400, maybe 50. This one goes all the way down to, let's say, 950, and this one stays up here at like I would estimate that to be, it's lower than 450. So I would say like this is like 500, this last one. Okay, and so now the shorter the bond length, the more it would be the distance, right? The distance would be less the shorter the bond length, right? And so two hydrogens, they're very small, right? H and H are very small. Their mass is very small. Mass is small. So off the bat, X would have to be H, because they only gave us three options. They gave us H, O, and N, right? So off the bat, any answer that doesn't have X2 as H, I'm eliminating. So off the bat, the answer cannot be C. So C is out the picture. And the answer cannot be D. So that kind of leaves us with two answers, right? And so with the same logic, if you look at a periodic table, oxygen is much larger, right? Out of these three, at least, it's the largest. And so then I would look here as oxygen being the largest. And so its line would be here, and this measures the internuclear distance. Because it is largest, it needs the most space, because they need to, accommodate for its space. And so I am picking the answer A. Okay, moving on. Okay, this one question asks the potential energy of a system of two atoms as a function of their internuclear distances shown below. Okay, so it's basically everything we've been looking at. This is just showing us our bond length, internuclear distance, right? Which of the following is true regarding the forces between the atoms when their internuclear distance is x? Okay. The attractive and repulsive forces are balanced. And so the atom will maintain an average internuclear distance. That sounds about right. The net repulsive force pushes the atoms apart. No. This is definitely not it. So when they are pushed apart, they would be here. This is when they are pushed apart. They would be up here. It would be generally here. And you see that in the other images earlier in the chapter. And here, this says there's a net attraction. Now, they're talking about right here. What is happening right here? The net attractive force is pulling the atoms together. So the atoms... No, that was happening right here. This is when they were pulled together. Too much so, right? Pulled together. They were up there. And so here is when they're ideal. It cannot be determined. That's also wrong. So this is wrong. This is wrong. And so here is when they are most balanced. And this is, again, right, where it is most balanced. And this is also where it is ideal. Right? So this is where you want to be at. Okay, next question. Oh, not so many questions in this chapter. Okay. Okay. So this question asks us, based on the data in the tables opposite, I don't know why they say it like that. Based on that table, the data in the tables opposite, which of the following statements provides the best prediction for the boiling point of NaCl? Now, off the bat, we kind of know it's hard to boil salt. You've probably never seen salt boiled. It's probably an extremely high temperature. So now we are comparing NaCl to NaF and MgO. And we got to figure out, is NaCl's boiling point more like this one or more like this one, and why? Right? So off the bat, we have to use and think about Coulomb's law. Now, here I have some space. So Coulomb's law is the force is proportional to Q1, Q2 divided by R squared. Okay, and so NAF, we know NAF as far as the charges go. So here, where can I write this? NAF, here, NAF. So we know F is like the most electronegative thing ever, right? So this is going to be negative and this is going to be positive. And then their sizes are also, let's see what their sizes are. The ionic radius, F is 133. This is 133. And so Na is 76. 76. So now the attraction here would be nothing too crazy. It would be positive times negative would be negative over 209. And so this would be the result for us. So it would be something negative for the charge, and because the combination of this is negative, right? And then the next one would be MgO, and MgO, let's see, MgO, right? MgO would be positive 2 because oxygen is negative 2, right? So here, this would be a mass or a distance of Mg. Oh, right here they tell you too, MgO is plus 2 and minus 2, right? So its charge at the top would be, negative times 2, because it'd be negative, negative 2 and positive 2 would be like negative 4. So it'd be very, very strong, right? And so that divided by 72 and 140 would give you this, negative 2 over 222. So this is much stronger. This is much stronger high because of the high charges, right? So this is much stronger. All right, so greater. But now we're kind of comparing it between these two, right? Now we have to look at NaCl. And we have to see, where does NaCl fall in all of this? So let's write NaCl. So off the bat, Na has a positive and Cl has a negative. So Na has a positive, Cl has a negative, and so positive and negative will give you overall negative, right? And therefore, now we have to look at Na, which is 76, and Cl, which is 181, and that is 257. So 257. So negative over 257. And so off the bat, just because of its negative charge, I would say the MgO is the strongest by far. So MgO is the strongest, and it's much greater than NAF. At least the boiling point would be, right? So the boiling point, right? So it would be NAF, because this is so strong, right? Because of its strength, right? Its strength of a force of attraction. That's what we just calculated here. Is that the force of attraction is so strong here. We put a super great sign here. Like I want to put emphasize it. Not greater than or equal to, but just like, this is very strong because of its forces are so strong. It's hard to break it up. So that's why the boiling point is so hard. It's hard to make it boil. So MgO would be here. And then I would say the next one would be NAF. And then it would be NaCl. And so NaCl would have a lower boiling point than NAF because its attractions are not as strong, and so it would be less than 1695. So NaCl will have a lower boiling point than NaF because of the Coulombic attractions are weaker, right? So yeah, so its attractions are the weakest, right? Whatever this negative charge is, it's being divided by 257, which is greater than either of these, right? This negative charge is divided by the masses or the radius of 209, and this one is double divided by 222. So this one is way stronger, this one is a bit weaker, and this one is the weakest. So I would say it's A. Okay, moving on. Okay, so the next question asks us, the lattice energy of a salt is related to the energy required to separate the ions. That makes sense. And if you look up here earlier in the chapter, they show you this, like, this lattice. And this lattice is just like a, like a big Rubik's Cube almost. And the stronger this is, right, the stronger this energy is, the harder it's to break these ions up. For the following pairs of ions, is the energy that is required to separate, for which of the following pairs of ions is the energy that is required to separate the ions the largest? So we're looking for which one needs the most energy to be broken. Right? And so, again, we're going to have to consider the forces of attraction, right? And when we use the forces of attraction, we are considering Coulomb's law. So Q1, Q2 over radius squared. And so, let's look at the first one, right? So Q1 and Q2. So this one would be 1, right? Because it's a charge of 1 and 1, right? And here's a charge of 1 and 1. And here's a charge of 2 and 2. And here's a charge of 2 and 2, right? So we have to find the product because you have to multiply these two, right? So the product here is, where you gotta multiply. You gotta multiply. You gotta multiply. So that also means this is much, much stronger. By the way, last question, I wrote 2 here. It should be 4 here, not 2. So yeah, I forgot that. I added them by mistake. But it still comes out the same answer. So 1 times 1 is 1, 2 times 2 is 4, 1 times 1 is 1, and 2 times 2 is 4, right? And so now this one is probably going to be the strongest, or this one is probably going to be the strongest energy that is required to separate the ions, which means that it would have the strongest attractive force. And so here we can imagine that the smaller the distance, the stronger the attraction. So now we can just look at the sizes based on its placement in the periodic table. So if we look at, so really this one has oxygen and this one has oxygen, so we don't have to consider them, right? It's really which one is bigger, Ca or Mg, and out of the one, whichever one is smaller, it's going to have the greatest attractive force. So let's see where Ca is on the periodic table, and let's see where Mg is on the periodic table. So Ca is here, and Mg is here. So Mg is smaller. It's the same in a lot of ways. It's in the same group, but Mg has one less entire ring. So Mg is smaller, and so because it's smaller, the radius is less, right? And if the radius is less, then this value makes the force higher. So the answer must be C. Okay. Because they have although they have out of all 4 of them, it has the highest charge, but the smallest distance in between. That's the big idea. That's the whole idea with Coulomb's law of attraction. Excuse me. Okay, so the melting point of MgO is higher than NaF. Explanations for this observation include which of the following? Is Mg2 more positively charged than Na plus? Yeah, right. It's a much stronger in it's much more positive, right? And so, okay, let's keep reading. O2 is more negatively charged than F, and O2 ion is smaller than F. So, what we need to keep our focus on is that they're asking us about melting point of MgO. And melting point increases when ionic attraction increases. Why, might you ask? If two bonds are very strong, right? They have a very strong attraction. Melting, it requires the disruption of this bond. And for that to happen, right, as the ionic attraction is higher and higher and higher, it's harder and harder and harder, and you need more, energy to break up and melt this item, right? This bond, and this ionic attraction comes from our good old Coulomb's law, again, which is, at this point, it should have been drilled into your head. F is proportional to the product of Q1 and Q2 divided by R squared. Say it with me, right? So the larger the attraction of the two, excuse me, and the lower the distance in between the two, makes the attractive force the highest. So first things first, Mg2 is much more positive than positively charged than Na. And why that helps with the melting point of MgO is because whatever Mg2 is bonded with, right, it's probably going to have a -2 charge, right? And whatever Na is bonded with is going to have a negative charge. So, 2 times 2, and we did this before, is 4, and 1 times 1 is 1. So this Mg2 would have, be an explanation for why the melting point is so high. So I'm putting a check mark for 1. So any answer that doesn't have 1 is automatically wrong. I don't know why this says D twice. Okay, moving on. The next one says O2, I presume there's a minus sign here because O2 would never be positive, is more negatively charged than F. And this is true as well. It's kind of obvious, right? It's twice as more negative. It's twice as negative as the F, right? And so naturally, Mg would be bonded with oxygen, and again here we have this 2 times 2. Oh, when you do this Q1 and Q2, what they don't write often is it's the absolute value. So it wouldn't be 2 times -2 like that. It would be the absolute value. So it would equal -4, and then the -4 would equal 4, and that would be the answer. Okay, so 2 is right as well. So any answer that doesn't have 2 would be automatically wrong. Okay, and then the last one is O2 ion is smaller than the F minus ion. And so this is not true because O2 minus has an extra electron. So like O, right? O normally has, let's say on its valence, because otherwise they're the same. Because if you look here, right? They're right next to each other. Right? They're right next to each other. So if something is O2, normally oxygen has 1, 2, 3, 4, 5, 6, right? And so this is O, and there's an F, or fluorine, would have 7. So 1, 2, 3, 4, 5, 6, 7. And if there's a negative charge here, it means it has one more, so it has 8. But there's a -2 charge here, right? So it'd be 1, 2. This would also have 1, 2, 3, 4, 5, 6, 7, 8. So this would also have 8. So they're actually equal. But oxygen has less protons. This one has one more proton. So oxygen, off the top of my head, has 8 protons, but fluorine has 9, right? So 8 and 8, whatever attraction that they have, 9 and 8 would have a greater attraction, right? Because these protons, there's 9 of them. They're pulling harder. So this is actually smaller. The fluorine is actually smaller due to the fact that there's 9, let's say, magnets and 8 magnets instead of 8 and 8 magnets. This would pull these electrons in closer. So this radius would be smaller than oxygen. So anything with the answer 3 would be wrong. So this is wrong, and this is right. And that is the conclusion of 2.2. Please check your answers and make sure your answers align. If you have any questions, feel free to let me know in class.